Alright guys, last video in our test 1 review for tomorrow. So let's see, we've got an existing load at 500 kVA. So a customer's got an industrial plant with an existing load of 500 kVA and the power factor is 75%. Now, the power factor is always going to be lagging because you're always going to have more motors than you do capacitors. They want to add some new machinery to the plant. So the new load that they're going to add is 225 kVA and the power factor is 85%. Again, lagging because it's motors rather than more capacitors. So we want to determine the new kVA requirements and the power factor rating for the plant once this new machinery is installed. So we could just add these guys up and be above, but we really want to see where the power factor lands. And obviously the power factor is going to be between 75 and 85%. The total kVA is going to be very close to if we just added these guys up. So we'll be very close to 725. But we'll need to find the total wattage and total kVA in order to find our new power factor. That way we can size our capacitors on the next page. So let's do this first thing, guys. Our existing power factor is 75%. So we've got an existing power factor of 75%. The angle that is going with that we'll find in 2 seconds. The kVA is 500 kVA existing. Anything over here on this column right here, this is going to be our kilowatts or our adjacent. And anything over here, this guy is going to be our kVARs or the opposite. Okay, obviously this guy right here is just as given. This is our kVA or the largest value in the circuit, and that's our hypotenuse. So for that guy, we've got 500 kVA, and our new load is going to be 225 kVA. And the new load has a power factor of 85%, so we'll drop that in there as well. Okay, so how do you find the angle there? Well, the angle is based off of the power factor, and the power factor is based off of cos. So here for any of these guys, we can take the inverse cos of whatever that power factor is. So in the case of 75%, we'll take the inverse cos of 75. And for 85, we'll take the inverse cos of 0.85, and we'll find each of those values there. Okay, so let's take a look at those guys. So we've got second function, cos of 0.75, close brackets, gives us an angle of 41.41 degrees. Okay, make sure your calculator's in degrees. Sometimes your calculator's going to radians and it gives you the wrong angle. So 41.41 degrees. Okay, so let's find this other angle, guys. We've got the inverse cos of 0.85, and we should find an angle that's a little bit smaller there. So we've got second function cos, and we're doing 0.85 this time. And that gives us an angle of 31.79. Beautiful. So we can drop those guys in there. So our 0.75 was an angle of 41.41 degrees. And this guy for the 85 is 31.79. Beautiful. So now we're going to tackle this the exact same way as we have been the other calculations, in that we have two vectors here that we have to add, and they're not happening at the same time. So now we've got to find the x and the y components for the first vector and the x and the y components for the second vector. So we're going to do that by doing the cos of the angle. So we found our angle to be 41.41 degrees. And we're going to multiply that by our 500 kVA. And for this guy, the y component for this first vector is going to be the sine of 41.41 degrees. And we'll multiply by our hypotenuse of 500 kVA. Okay, let's bring this over here so we can see what we're doing. So we've got the cos of 41.41 degrees, and we're going to multiply that by 500. That gives us 374.98. Okay, then we'll find the y component there. So we need the sine of 41.41 degrees, close brackets, times our 500. That gives us 330.72. Beautiful. For the next guy, we're going to find the x and the y components for our second vector. So x of b is equal to the cos of 31.79 degrees. We're going to multiply that by 225. And here for our second vector, or our y component for our second vector, we're going to do the sine of, what is that, 31.79 degrees. We're going to multiply that by 225 kVA. Okay, so we've got the cos of 31.79. Multiply that by our kVA of 225. That gives us 191.25. Okay, and then we're going to take the sine of 31.79, multiply that by our hypotenuse of 225 kVA. That gives us 118.53. Excellent. Okay, at this point we're going to add these values up. All right, so going down here, we're just going to add them up, because now they're on the same plane. So now we can add those values. So our x component for our resultant here is going to be equal to 374.98 plus 191.25. Our y component for the resultant is going to be equal to 330.72 plus the 118.53. Okay, let's bring up our calculator here. So for our x component, we've got 374.98, and we're going to add the 191.25. That gives us 566.23. Okay, our y component for our resultant vector is going to be 330.72. Oh, sorry guys, 330.72 plus our 118.53. That gives us 449.25. Okay, at that point, going back, we have an x component and a y component. These guys are 90 degrees out of phase. So going back this way, we're now going to use Pythagoras. Okay, so we've got 566.23 squared. So for our new kVA right here, we're going to have 566. What's going on with my pen? Hang on. 0.23. We're going to square that value plus our 449.25 squared. Then we're going to take the square root of those values. Give me 2 seconds to pump that into the calculator. Okay, so I put in my 566.23 squared plus my 449.25 squared, and I take the square root, and I find a value of 722.8. Okay, so you can see that here, if I just added these guys up, I'd have 725. So why did I go through all this work in order to find those values? Well, now that we found our kVA, and here we found our kilowatts, right? These guys here are essentially our kilowatts. These guys are our kVARs. At that point, we can find our combined power factor. And our combined power factor is going to be somewhere between 75 and 85% efficient. Okay, so for that guy, we can find our new power factor, or our combined power factor. We've got 566.23 kilowatts over 722.8 kVA. And let's see what that ratio is, guys. So what have we got? We got 566.23 divided by 722.8, and that gives us 0.78 for our new combined power factor. Okay, don't worry about the angle here. I mean, if we want here, let's find the angle quickly, right? But that angle there would be equal to the inverse cos of that power factor at 0.78. And so if we find that quickly here, let's clear this out. So we'll do second function cos, and we'll do 0.78 for our combined power factor. That angle is going to be somewhere between 31 and 41 degrees. So 38.74 degrees. Okay, that's kind of inconsequential. We're going to use this new combined power factor on the next page there. All right, so stop the video here, guys. Make sure that everything's cool. We're now going to transfer our kilowatts over to the next page. So we have 566.23 kilowatts. Okay, so when we do power factor correction, the kilowatts doesn't change, right? That's basically the power that's lost in the form of heat and light. So our kVARs is going to change, and by changing our kVARs, it's going to change our kilowatts, but our kVA, but our kilowatts is going to stay essentially the same. So from the previous page, let's go back and see what our power factor is. Okay, so we can see right here that our combined power factor from the previous page was 78%. So let's transfer that over to the next page. Okay, so we need to go from a power factor of 0.78, right, because our combined power factor there was 0.78, and we're going to fix that to a power factor of 95%. Remember that anything below 90%, you're going to have a surcharge on your electrical bill. So we're going to bring this up to 95%. Now, before when we were doing these things with the single phase, we were having to do sine, and we were doing all kinds of calculations using Pythagoras in order to find the size of capacitors. Everything's done in a chart. That previous portion was just to show you how that chart was created. So let's bring up that chart now. Okay, so here's our chart. If we go back here, our values are going from 0.78 to 0.95. So here's our original power factor right here. And we're looking for a value of 0.78 or 78%. And we're going to go to a desired power factor of 95%. So all the calculations have already been done for us. All we have to do is just follow this down and follow this column right here, or this row, I guess, right across until the two meet. And it looks like our multiplier here is going to be 0.473. Okay, if you're wondering what you're going to multiply that 0.473 by, at the bottom of the chart, it tells you that this chart is the kilowatt multipliers for determining our capacitive kVARs. Okay, so we're going to multiply that multiplier by our kilowatt value. Okay, so just remembering that our value is 0.473. Okay, so our multiplier there is 0. Let's put that in a different color here so we can distinguish it. 0.473, and we're going to multiply that by 566.23 kilowatts. Okay, so let's see, we've got issues with the calculator. Come on, buddy, work with me. So we got 0.473 times 566.23, and that gives us 267.83. And just by doing that, that's going to give us the size of our capacitors. Now these come in 10,000 vars units, so this would basically be 270 kVars of capacitance. Okay, so just to go through all the different steps that we did, we found our initial power factor of 0.78 from our previous page, combining those two loads, our existing load and our new load. We brought that over to this page in addition to our existing kilowatts. This value will not change whatsoever, and we're going to try and fix the power factor to 0.95. We found this multiplier, 0.473, from our chart, looking at our existing power factor and our desired power factor, and we multiplied that by our kilowatts in order to find the size of our capacitor bank. So now that we've done all that, now we can find our new kVA once we've put these capacitors in. So if we look at our previous kVA, let's just bring that up. Our previous combined kVA was 722.8 kVA. So we had our old kVA at 722.8 kVA, but that was before we put in this capacitor bank. Once we put in this capacitor bank, then we'll find that our kVA value is going to drop. So we still know that the relationship for power factor is watts over VA, so we can do kilowatts over kVA. And if we're trying to find our new kVA value, so with the capacitor bank, then it looks like we're going to take our kilowatts and divide it by our new power factor. So we're going to take our 566.23 kilowatts. We're going to divide by our new power factor of 95%. And that'll give us our new kVA. Okay, so we got 566.23 divided by 0.95, and that gives us 596 kVA. So you can see the significant difference. Once we put these capacitors in, our combined kVA from the existing load and the additional load was 723 kVA. Now that we put in this capacitor bank, our new kVA is 596 kVA. So maybe this has just opened up a window here where by putting in the capacitors, we can do the additional load and we can still make use of the existing service and the existing transformer. So in doing so, maybe you're going to get the contract for the additional load, and you're also going to get the contract for this capacitor bank, because this capacitor bank is going to pay for the initial installation of the additional load over like 3 or 4 years, right? Because they're saving this much power every year. All right, guys, that's it for the test review. Thank you very much for all your patience in going through all these questions. You should do great on the test. It's primarily just the relationships of the Y and the delta, and then we're going to have a neutral current calculation, a three-phase RLC circuit calculation, and now a three-phase power factor correction calculation. Everything will be provided for you in these charts, identical to the review that we've just done. All right, guys, thanks very much. Good luck on the test.